Hello there, and welcome to Sleepy Cosmic Podcast, where quiet curiosity meets the night and wonder is allowed to take its time. Somewhere out there, beyond the warm cradle of our home planet, lie worlds cloaked in silence. Moons that drift far from their suns, cloaked in velvet darkness, where light arrives in faint whispers and time feels impossibly slow. These are places of ice, of long shadows, and of stories still waiting to be heard. Tonight, we'll listen for one such whisper, the kind that might rise softly from beneath frozen crusts, a breath of water, of ammonia, of something ancient and cold. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe, no pressure at all. And if you feel like sharing, I'd love to know where you're listening from, and what time it is for you right now. Now dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We begin with a question that feels both simple and wondrous. How would we even know if somewhere out there a cryovolcano is still breathing? The word volcano usually calls to mind fire and fury, molten rock, ashes billowing against the sky. But cryovolcanoes belong to a different world, a colder world. Here, eruptions are not of fire, but of ice, not lava, but slush. They do not roar, they sigh. And these sighs, if they still happen, are extraordinarily quiet. On distant moons like Enceladus, Triton, or Pluto, there's barely an atmosphere to carry sound. A geyser might erupt and vanish into the vacuum unnoticed unless you're watching with just the right eyes, in just the right light. Still, we wonder, do these icy breaths still happen today? Or are they memories frozen into the crust? Remnants of an era now gone still? The question lingers, because if cryovolcanoes still breathe, it means something within these cold moons is still alive, not with life as we know it, but with motion, with heat, with chemistry, with story. The most vivid evidence we've seen comes from Saturn's small moon Enceladus. We'll visit it more closely later on. But even before Enceladus, even before Cassini sent back glittering images of icy plumes arcing skyward, the idea of cold volcanism was already drifting through scientific thought. In the 1980s, when Voyager 2 sailed past Neptune, it turned its camera toward Triton, and there, in the shadowed terrain of that distant moon, it saw something strange, black streaks, arcing from the surface. Patterns that looked suspiciously like geysers. No one had expected it. Neptune was so far away, so cold, and yet, there they were, signs of eruption. They weren't fiery fountains. These were likely nitrogen geysers, rising only a few kilometers before the gas froze again and drifted down like a whispering snowfall. Still, it was enough to suggest something extraordinary. Even at the edges of the sun's reach, motion still happens. We now think of cryovolcanism not as a rare anomaly, but as a quiet language, a way the outer solar system might express its hidden dynamics. Instead of molten basalt, these volcanoes might eject water, ammonia, or methane, warmed just enough by subtle heat sources within. Tidal flexing, internal radioactivity, or lingering formation warmth could create pockets of slushy material beneath the surface, just waiting to escape. And unlike Earth's volcanoes, which erupt with drama and finality, cryovolcanoes might be slow and patient. They may ooze, they may seep. Some may erupt only once every 1,000 years. Others may pulse with more regular rhythm, breathing in and out with the gravity of their parent planets. Imagine standing on such a moon, perhaps Pluto, perhaps Ceres. The horizon is low, the sky starless black. Beneath your feet, ice stretches in every direction. Then, without sound, a plume of vapour begins to rise, not violently, just steadily. A column of faint mist climbing silently toward space, lit softly by the distant sun. If you weren't looking right at it, you might not notice it at all. But in that quiet moment, The surface has spoken. That's the essence of cryovolcanoes. Not destruction, but expression. Not fire, but breath. It's important to remember, though, that not every strange feature on an icy moon is necessarily volcanic. Some may be the result of ice tectonics, where crusts shift and crack. Others could be formed by impacts, or sublimation, or simply the slow passage of deep time. Astrophysicists still debate whether certain features, like the smooth plains on Pluto or the ridged terrain on Europa, are truly volcanic in origin. It might depend on how you define a volcano. Is it any geologic release? Does it need to erupt? Must it build a mountain? On these frozen bodies, the answers are still being shaped, but even in the face of uncertainty, the idea draws us in. Because if cryovolcanoes are still active, if they're not just relics but living systems, then beneath those crusts something is stirring. Heat, pressure, motion. And where there is motion, there might also be change. Complexity, perhaps even the chemistry of life. So we begin our journey by listening closely, not for a roar, but for a sigh, a shimmer, a plume in the starlight. If cryovolcanoes still breathe, then maybe, just maybe, the coldest corners of our solar system are not as silent as they seem. Cryovolcanoes. The word sounds familiar and alien at the same time. A volcano made not of fire, but of ice. It's a concept that seems to bend the very definition of eruption, turning everything we assume about planetary heat inside out. On Earth, we think of volcanoes as violent and fiery. Magma boils from deep chambers, pressure builds, and when it can no longer be contained, the crust cracks open. Lava pours out, reshaping the land, sometimes changing it forever. But in the far reaches of our solar system, where the sun is a dim star on the horizon, heat is rare. Temperatures hover hundreds of degrees below freezing. Here, molten rock would freeze solid in seconds. But ice can behave differently. Under the right conditions, ice becomes lava. Not the kind that glows red and burns to the touch, but slurries of water and ammonia, of methane and nitrogen. These are volatile compounds, and when warmed just enough they can melt and rise, flowing through fractures in the crust like slow, syrupy ghosts. A cryovolcano is born not from fire, but from internal stirrings deep within an icy body. Pressure from tidal forces or heat from radioactive decay causes subsurface pockets to warm. In time, these pockets expand, and with nowhere to go, they seek a path upward. The crust may yield slowly, a crack forms, a vent opens, and from it, a plume of vapour rises, not with a boom, but with a hush. Cryovolcanism, at its heart, is about geology in slow motion. It's a process shaped by time, chemistry, and patience. Where a fire volcano may erupt in minutes, an icy one might take centuries to prepare its gentle breath. What makes a cryovolcano so different is not just what it erupts, but how it leaves its mark. On moons like Enceladus, jets of water vapour carve grooves into the ice. On Pluto, frozen nitrogen may pool into vast, smooth basins, as if poured like syrup across a cosmic pancake. And unlike Earth's volcanoes, which often tower as mountains, many cryovolcanoes are subtle. Some are merely domes or shallow depressions. Others, like those suspected on Ceres, are ghostly mounds barely distinguishable from the surrounding terrain. But they tell a story that suggests movement in a place we once thought frozen solid. Let's imagine a specific cryovolcano, not a real one, but a composite, a soft sculpture in our minds. Picture a smooth plain of nitrogen ice under a darkened sky. Low hills stretch in gentle curves, and there, at the centre, a dome, a raised swell just a few kilometres wide. From its summit, faint streaks radiate outward, as if something once flowed gently across the surface, now frozen in place. No smoke, no fire, just the memory of warmth. This is a cryovolcano, at least one version of it. Another might look entirely different. Some may erupt beneath a crust of ice, hidden from sight, only their chemical traces seeping to the surface. Others might punch through with jets that sparkle faintly in sunlight, like those seen on Enceladus. What unites them is not appearance, but process. Cryovolcanism requires three things: volatile material, like water or ammonia, an energy source, heat, however faint, and a way for pressure to escape. On icy moons, water doesn't just exist as solid ice. Beneath certain conditions, it may remain liquid, especially if mixed with salts or ammonia, which lower its freezing point. These pockets of slushy brine can remain for millions, even billions of years. If pressure builds within these pockets and the crust above weakens, perhaps from impact, tidal strain or temperature shifts, then the material can rise. In this way, a cryovolcano may not just erupt, it may breathe. Slowly, gently, rhythmically. This isn't just poetic language. Some scientists suspect that cryovolcanoes might work in cycles, that the forces causing them to erupt could wax and wane with orbital alignments, with internal convection, or with changes in the overlying crust. They may be active for a while, then quiet for centuries, then active again. And unlike lava, which hardens quickly, icy plumes may vaporize, condense, and settle back as snowfall. In some cases, the eruption itself becomes invisible. What's left is a thin film, a blanket of new frost, a change in reflectivity. These are subtle clues, which is why detecting cryovolcanoes is so difficult. We're often not looking for smoke and ash, but for spectral fingerprints, slight shifts in surface colour, tiny changes in elevation, or faint plumes caught by starlight in just the right moment. Even with all our tools, we still might miss them. That's why scientists often look for indirect signs. Is the surface young? Are there few craters? Are there patterns in the ice that suggest upwelling from below? Is there thermal imaging that shows a spot warmer than it should be? From these fragments, we build the case. But the debate continues. Not all icy anomalies are cryovolcanoes. Some might be landslides or tectonic stretching. Others could be tricks of lighting or erosion. And so, we remain careful. The label cryovolcano is used with caution. It's a hypothesis, not a declaration. But still, it beckons. Because if these features truly are cryovolcanoes, then the worlds that hold them are not dead. They are alive in their own quiet way. They shift, they pulse, they breathe. And in that breath there might be something more. A message from deep time, a sign of hidden chemistry, perhaps even someday a whisper of life. For now we listen, we watch, we wait. Among all the icy moons in our solar system, one glows softly in the dreams of astronomers more than most. Not because it is big, not because it is old, but because it speaks. Enceladus. Just 500 kilometers across, small enough to fit inside the borders of a modest country, Enceladus orbits Saturn in quiet grace, wrapped in bright white ice that reflects almost all the light it receives. It's one of the most reflective objects in the solar system. From a distance it gleams like a snow-covered pearl adrift in the void. But beneath that brightness there is movement. In 2005, the Cassini spacecraft, on its long and unhurried tour of the Saturnian system, passed close to Enceladus. What it saw changed our understanding of the moon forever. There, near the South Pole, were unmistakable plumes, jets of water vapour and ice particles shooting hundreds of kilometres into space. Not just once, repeatedly. The discovery wasn't expected. It wasn't even on the mission's checklist. Enceladus had been considered cold and dead. Perhaps pretty, but not particularly interesting geologically. And yet, here it was, breathing. Soft fountains arcing silently against the black, eruptions without fire, jets without sound, cryovolcanoes. Cassini didn't just observe them, it flew through them. Instruments on board tasted the plumes, measured their speed, analysed their composition. What they found was simple and astonishing. Water, mostly, but also salts, organic molecules and traces of ammonia. Not proof of life, but proof of ingredients. Proof of warmth, proof of possibility. The jets seemed to emerge from long fissures in the icy crust, later nicknamed tiger stripes. These fractures, named things like Damascus sulcus and Baghdad sulcus, run for hundreds of kilometres, cutting through the South Pole like old scars. But these scars are warm. Cassini's instruments showed temperatures far higher than expected, still cold by Earth standards, but much warmer than the surrounding ice, enough warmth to keep water liquid beneath the surface. We now believe that under Enceladus's crust lies a global ocean, a hidden sea sandwiched between icy shell and rocky core, a sea that may be in contact with rock where chemical reactions could occur, a sea that, through these fissures, vents its breath into the void. The scale is breathtaking. Imagine, beneath this tiny moon, a vast ocean sloshes quietly, and through its icy skin, the ocean exhales, sending vapor and ice crystals into space, where Saturn's gravity helps sweep them into a vast ring. In fact, much of Saturn's E-ring is made of Enceladus's size. All of this, from a world no one expected to speak. The plumes themselves seem to be shaped by gravity. Tidal forces from Saturn stretch and compress Enceladus as it orbits, opening and closing the fissures slightly. The moon's crust flexes just enough for water to escape. It's a kind of cosmic breathing, slow, rhythmic, gentle. And with each exhale, a message is sent. A message not just of geology, but of potential habitability. Enceladus, more than any other world in the outer solar system, invites the question, could something live here? We don't know, but the signs are promising. We know that life as we understand it requires three main ingredients: liquid water, a source of energy, and the right chemistry. Enceladus may offer all three. Liquid water, almost certainly. An ocean warm enough to remain unfrozen, salty enough to resemble Earth's own seas in some respects. Energy, the tidal forces from Saturn provide it. And if the seafloor is rocky, chemical reactions between water and rock, known as serpentinization, could offer further fuel, creating hydrogen gas and supporting potential microbial life. And chemistry. Cassini detected organic molecules in the plumes, not life itself, but the building blocks, carbon-based compounds, the alphabet of life, scattered in vapor across the stars. Some scientists now dream of a future mission, a probe designed to orbit Enceladus again, to fly through the plumes with even more sensitive instruments, perhaps even a lander to study the tiger stripes directly. Maybe one day we'll lower a robotic submarine into that dark, hidden ocean. But for now, we have Cassini's data, and that's enough to let us dream. Still, there are uncertainties. Some researchers wonder if the ocean might be more like a regional sea, confined to the South Pole. Others debate the depth of the ice shell or the long-term stability of the vents. Astrophysicists still debate whether the plumes we see now are steady or just a phase, perhaps tied to an orbital cycle, or even a rare window in the moon's history. Some suggest the cryovolcanism we see now is just a brief whisper, a geological blink, a lucky moment in time. If so, we are fortunate to have witnessed it. Because what Enceladus offers us is rare, an active, speaking moon, one that tells us, in its soft and icy way, that even in the coldest places change still happens. Even in deep space, water still flows. And when water flows, our curiosity follows, gently, quietly, unhurried. We return again and again to Enceladus, not because it's large or bright or central, but because it reminds us that even a small world, barely visible in a telescope, can harbour deep mysteries. It's a lesson in humility, a reminder that life's potential might be hiding not in grand landscapes, but in quiet, cold corners. And it leaves us with a simple, enduring question. If Enceladus whispers, who else might be listening? Right. Europa drifts quietly around Jupiter, trailing its soft, icy scars behind it like pages of a slow, unfolding story. Slightly smaller than our moon, Europa holds one of the most profound secrets in the solar system, one that may ripple softly beneath its fractured face. From afar, Europa looks deceptively smooth. Its bright surface reflects sunlight well, giving it an almost luminous appearance. But as we drift closer, we see a world crisscrossed with fine brown lines, ridges, fractures, and long scars etched into the crust like veins in marble. These lines are not just random patterns, they are clues. Europa's surface is a frozen shell, but beneath it lies an ocean, deep, global, and likely twice the volume of all Earth's oceans combined. And those lines, they are where the shell has cracked, shifted, groaned in the cold. They are where something below may be pushing gently upward. For decades, Europa has intrigued planetary scientists. The Galileo spacecraft, which orbited Jupiter in the 1990s and early 2000s, passed close to Europa multiple times. It detected a magnetic signature, suggesting a salty, conductive ocean beneath the crust. Later flybys revealed surface features that seemed to have been created by rising plumes or oozing slurries of ice, textured areas where the crust appears to have broken and been replaced. The most tantalizing hint came more recently. In 2012, the Hubble Space Telescope observed faint plumes of water vapor rising above Europa's south polar region. Not large and not sustained, but present. Observed again in 2014, and possibly in earlier archival data, these hints suggest that Europa too may be breathing. Softly, intermittently. If these plumes are real, and not observational artifacts, they may be cryovolcanic in nature. And if that's true, then Europa is not just a frozen orb, but a dynamic world where ocean water breaks free and escapes into space. And that changes everything. It means we might study Europa's ocean without drilling through kilometers of ice. We could in theory fly a spacecraft through the plumes, as Cassini did at Enceladus, and collect samples directly from the hidden sea. That mission may already be on its way. NASA's Europa Clipper, set to launch soon, will orbit Jupiter and perform dozens of flybys of Europa. Its instruments are designed to confirm the presence of plumes, measure their composition, and map the structure of the icy shell. But questions remain. Are the plumes truly cryovolcanic, or are they the result of some other process? Could they be episodic, perhaps triggered by tidal stresses or shifting ice plates? Or are they a temporary phase in Europa's long geological life? Astrophysicists still debate the exact mechanisms. The ocean beneath may be heated by tidal flexing, but its interaction with the icy shell is complex. Cracks may open and close, chambers may fill and drain. Pressure may build slowly, only to release in brief, silent bursts. Cryovolcanoes on Europa might not be towers or cones, but simple vents, narrow fissures where ocean water, laced with salts and organics, escapes through the crust. And if these vents exist, they may be ancient or new, persistent or fleeting. Some may only erupt once in 1,000 years. Others may sigh gently, continuously, unnoticed except by the most sensitive instruments. From the surface there would be no sound. The atmosphere is far too thin to carry it. But the plume would rise nonetheless, a silent beacon in the night. Europa's surface too tells stories. Some regions show chaos terrain, areas where ice appears to have melted and refrozen in jumbled blocks. These regions may mark places where the ocean came close to the surface, or even broke through, flooding and freezing anew. Others show double ridges, raised lines with central valleys that resemble formations seen in Earth's polar ice sheets. Recent studies suggest these may form through repeated refreezing and pressure cycling, driven by liquid water moving just beneath the crust. And that brings us to a beautiful, quiet possibility, that the icy shell is not a rigid, unchanging block, but a living system, shifting, melting, refreezing, breathing. Perhaps cryovolcanism on Europa is not dramatic but intimate, not rare but hidden. The surface may appear static, but beneath, a dynamic interplay of ocean and ice may be constantly at work, too slow for our eyes, too quiet for our ears, but real. That's the wonder of Europa. It holds its secrets in stillness, but those secrets are not static. They are waiting. Perhaps one day a spacecraft will glide through a rising plume, and in the crystals it collects we'll find more than water. We'll find salts, amino acids, maybe something more. For now, we wait and listen. Europa doesn't roar, it hums, and we are learning how to hear it. Pluto drifts at the edge of everything, orbiting far beyond the gas giants in a region of slow revolutions and long winters. For decades, it was a distant point of light, mysterious and unresolved. Then, in 2015, the New Horizons spacecraft swept past it, offering us our very first close look. What it revealed was not a frozen, dormant rock, but a surprisingly complex world, a place sculpted by ice and shadow, with plains and mountains, ridges and valleys, and at its heart a feature both unexpected and oddly beautiful, a vast, smooth basin shaped like a soft, asymmetrical heart. It's called Sputnik Planitia. Stretching 1,000 kilometers across, Sputnik Planitia is not just visually striking, it's scientifically puzzling. Its surface is remarkably young, with almost no visible impact craters. That suggests something rare in such a distant world. Geological activity. A surface still changing. But there's more. Sputnik Planitia is not made of a rock. It's a frozen sheet of nitrogen ice, mixed with a touch of methane and carbon monoxide. And that ice, despite the biting cold, appears to be moving. Not quickly, not like glaciers on Earth that crack and thunder, but slowly, softly, over millions of years, like a breath drawn out across epochs. The ice convects, it cycles, it rises, spreads and sinks. Driven by the faint warmth of Pluto's interior and the physics of frozen nitrogen, it behaves almost like a sluggish sea. And beneath that sea of ice, perhaps more. Some models suggest Pluto may harbour a subsurface ocean, an inner sea, insulated by layers of ice and warmed by radioactive decay in its rocky core. If that ocean still exists, it might be responsible for lifting and cracking the surface, reshaping the terrain in slow cyclical waves. Cryovolcanism may be Pluto's way of speaking. Elsewhere on Pluto, New Horizons found other signs. Strange, rounded mounds, some rising 6 kilometers high, dot the landscape. These features such as Wright Mons and Picard Mons are massive, but they are unlike any mountain seen before. They don't appear to be made of rock. They lack the sharp edges typical of tectonic uplift. Instead, they look like frozen flows, built up slowly over time. Some planetary scientists believe they could be cryovolcanoes, formed by repeated eruptions of icy slush that solidified and built up over time. Unlike traditional volcanoes that glow and boom, these might have seeped and slumped. Their structure is uneven, their surfaces weathered and scarred. But their shape, rising mounds with central depressions, suggests upwelling. And perhaps very long-lived activity. Still, there is uncertainty. Astrophysicists still debate whether Pluto's surface features are truly volcanic. Some argue that the mounds could be remnants of other processes, slow uplift or collapsed voids. But if cryovolcanism is indeed responsible, it would mean Pluto, despite its distance and small size, is not just geologically alive, but uniquely so. It also raises deeper questions. What does it mean for such a small world to hold heat, to shape itself over time, to breathe, even softly? One possibility lies in Pluto's internal structure. While it's far from the Sun, its interior contains radioactive elements like uranium and thorium. These decay slowly, releasing energy. Over billions of years, that heat may have built up, warming the core and melting surrounding ice. With enough insulation from the icy outer shell, a subsurface ocean could remain liquid even now. That ocean, pressing upward, could fracture the crust, and through those fractures, icy material might rise, erupting not in fire, but in frost. Unlike Europa or Enceladus, Pluto doesn't have a large planetary body to tug on it with tidal forces. Its main moon, Charon, is relatively close in size, and the two are tidally locked, always showing the same face to each other. That dance creates stability, but it may also produce subtle flexing deep within Pluto's core, just enough to maintain slow internal movement. And if that's true, the heart of Pluto may still beat, not rapidly, not dramatically, but slowly, like a whisper in deep space. New Horizons only gave us a brief glimpse, a few hours of flyby time. We've never seen Pluto again in such detail, and yet, in that fleeting encounter, the moon shared secrets it had held for billions of years. It showed us that cold does not always mean stillness, that distance does not mean silence, and that even at the edge of the solar system, geology continues its slow, sculpting work. Somewhere beneath Sputnik Planitia, perhaps right now, a pocket of nitrogen ice is rising. Perhaps a crack is opening in the crust, just wide enough for vapour to escape. Or maybe nothing at all is happening. Maybe the heart has gone quiet again. We cannot know for sure. But the possibility remains, and in that possibility we find wonder, because if Pluto, a world so small, so far, can harbour hidden oceans, quiet eruptions, and slowly shifting plains, then the cosmos may be richer, softer, and more alive than we ever imagined. In the darkness, even silence can speak. Between the orbits of Mars and Jupiter lies a curious world that seems to sit at a crossroads, neither quite a planet nor just an asteroid. It's called Ceres, and for a long time it was easy to overlook. Small, faint and round, Ceres gently drifted through the asteroid belt without making much noise. But then came dawn. NASA's Dawn spacecraft, launched in 2007, arrived at Ceres in 2015 after a long, spiralling journey through the inner solar system, and as it approached, the surface of Ceres revealed something strange, something no one had expected. Bright spots, tiny, brilliant flashes of white set against the dark grey surface, like sequins scattered across a slate. At first, astronomers were puzzled. Was it ice? Salt? Reflection? The answer, as it turned out, was both simple and mysterious. The brightest of these spots lies within a large crater named a crater. Nestled in its centre is a region called Cerealia Facula, a patch of sodium carbonate, a kind of salt left behind when briny water evaporates, and around it, other smaller patches, called Venalia Faculae, form a gentle ring. But what's truly fascinating isn't just their brightness, it's their youth. Spectral analysis and surface modelling suggest these bright spots are relatively recent. Perhaps only a few million years old, perhaps younger still. Some scientists believe that briny water from beneath the surface seeped up through fractures and then froze, leaving behind these salt deposits as the liquid evaporated into space. In other words, Ceres may have cried, not loudly, not often, but enough to leave behind trails of salt, soft tears from an ancient ocean deep below. And those aren't the only clues. Dawn also detected haze-like mists in Orcator crater, faint, localized fogs that formed briefly in sunlight and faded with shadow. These might be remnants of sublimating ice, or thin vapor venting from below. Nothing dramatic, just a whisper, a breath. This gentle exhalation suggests that cryovolcanism on Ceres may be ongoing, or at least recent. The crust may still be shifting. Brine may still be seeping upward. The surface, though quiet, may still be changing. It's a remarkable idea, especially for a world with no atmosphere to speak of and temperatures well below freezing. But something beneath Ceres seems to retain warmth. Some models suggest the dwarf planet still holds a deep, muddy mantle, part rock, part ice, perhaps with pockets of salty liquid left over from its early formation. Cryovolcanoes on Ceres, if they exist, would look nothing like those on Earth. They might not even look like the mounded domes of Pluto. Instead, they might resemble simple fractures, long, narrow cracks where brine wells up and freezes in place. Or, as with a feature named Ahuna Mons, they might form solitary ice domes. Ahuna is a lonely mountain, rising about 4 kilometers above the surrounding terrain. It's relatively smooth and lacks the cratered scars of older features. Scientists believe it may be a cryovolcano, a frozen blister that formed from a single, slow eruption of salty ice. It's the only structure like it on the planet, and it seems young. Perhaps only 200 million years old. That may sound ancient, but on planetary timescales it's still warm. The question, of course, remains, is Ceres still active, or have its internal waters frozen solid, never to flow again? Astrophysicists still debate this gently. Some think the heat is gone, the crust hardened. Others point to the salts, the haze, and the shape of Ahuna Mons as signs that the interior still holds potential. That even now in shadowed places brine stirs, and that has implications beyond geology. Salty water, in contact with rock, can create chemical gradients, conditions where energy flows and molecules mix. On Earth, these places, hydrothermal vents, are teeming with life. Strange, resilient life that thrives without sunlight, feeding on minerals and warmth. Could Ceres offer the same? We don't know. But the presence of water, salts, and potential heat makes it one of the more intriguing places to search. And there's something poetic about it too. Ceres was once the largest asteroid, then the first dwarf planet visited by a spacecraft. It sits in a liminal space between planets and rubble, between warmth and cold, between silence and motion. It doesn't shout, it hums. If cryovolcanoes do exist there, they are not eruptive, they are expressive. They leave their messages not in smoke but in crystal, not in lava but in salt. And those messages take time, thousands or millions of years, to form and to fade. But they remain, glinting faintly in sunlight, reminding us that even small worlds, even quiet ones, have stories to tell. Perhaps on some distant morning, a new spacecraft will descend through the quiet of space and land beside one of Ceres's bright spots. It will scoop up the salt, taste the minerals, listen to the ground, and maybe, just maybe, it will hear the echo of something moving deep below. Triton drifts far out in the shadowed kingdom of Neptune, circling its host planet in the wrong direction. It's the only large moon in the solar system with a retrograde orbit, a sign that it likely didn't form where it now floats. Instead, Triton may have been captured long ago, a wanderer drawn into Neptune's cold gravity, its past gently erased by tides and time. Even now, Triton remains mysterious. Only one spacecraft has ever passed close to it, Voyager 2 in 1989. A brief encounter lasting mere hours, but long enough to offer a glimpse into something quietly extraordinary. Triton, it turned out, is not the dead rock we once imagined. Voyager's cameras revealed a surface strangely smooth in places, marked by pits and dark streaks, not covered in craters like most old moons. Instead, there were signs of change, of renewal, of something stirring beneath. And then, in the unfiltered frames of a world never seen before, Voyager captured a plume, a geyser, It wasn't bright or explosive. It didn't pierce the sky with colour or sound, but it was real. A dark plume rising as high as 8 kilometres, then bending in the thin atmosphere, trailing for over 100 kilometres downwind. This was no firework. It was a hush, a breath of nitrogen gas and fine particles, escaping through a vent and sweeping softly across the plains. Triton, it seemed, was crying out, quietly. These plumes are likely driven by solar heating. What little sunlight reaches the surface can warm a dark patch of ice just enough to cause gas to build up beneath the translucent shell. The pressure increases until, crack, the gas escapes, carrying with it a mist of dust and ice. This isn't cryovolcanism in the traditional sense. There's no subsurface ocean breaking through a thick crust, no deep mantle stirring with ammonia or slush. But it is, in its own way, a kind of frozen volcanism, powered by light, not heat. A faint, cold exhalation. And Voyager didn't see just one plume, it saw several. In a world where temperatures plunge below 230 degrees Celsius, Triton's activity was unexpected, gentle but undeniable. Later observations hinted at even more strange features. Cantaloupe terrain, they called it, a texture of rounded hills and pits, like the skin of the fruit. This terrain likely formed through cryovolcanic processes, though their exact nature remains unknown. Some scientists propose that liquid or slushy ices, perhaps composed of ammonia and water, once welled up from beneath and froze in undulating patterns. Other regions display smooth plains, young geologically speaking, suggesting that the surface has been renewed, perhaps repeatedly. These hints paint a picture of Triton as a moon shaped by cold flows and slow breaths. Its retrograde orbit causes tidal stresses that may, even now, warm its interior slightly. This warmth might keep a layer of ices, water, methane, nitrogen, just soft enough to flow or erupt under the right conditions. But that's still an open question. Astrophysicists still debate whether Triton is cryovolcanically active today, or if its signs are remnants of a past age. The Voyager data is old now, limited in resolution and scope. No new spacecraft has visited Neptune since, and so Triton remains distant, its voice muffled by distance and time, but its pull is strong. Of all the large moons, Triton is the only one with a confirmed plume seen outside the Saturnian system. Its surface chemistry is rich and strange. It has a thin atmosphere made mostly of nitrogen, with a whisper of methane, and its orbit, slowly spiralling inward, suggests a future where it may someday break apart and form new rings around Neptune. Triton is not a moon frozen in place. It's a world in motion, even if that motion is glacial. Its landscapes bear the marks of processes we're only beginning to understand. Its geysers whisper of pressure and release, light and shadow, surface and depth. One day, perhaps, a mission will return, a spacecraft built not for flybys, but for lingering, for listening, for watching the slow dance of Triton's seasons and tracing the ghost trails of its plumes. There may still be cryovolcanoes hidden beneath its crust, vents that open for brief periods, then close again for centuries. Or there may be only the slow sublimation of nitrogen, rising softly with each sunrise. Either way, the story is not over. Triton reminds us that even the coldest places can speak in movement, that even silence can swell into motion, that even moons stolen from other orbits may still carry their own quiet purpose. In the hush between Neptune's winds and the long echo of Voyager's passage, Triton waits, not asleep, not loud, just whispering. When we think of something flowing, we often picture water or lava, materials that respond easily to heat and gravity. But in the outer reaches of the solar system, where warmth is scarce and the air is almost non-existent, what does it mean for something to flow? Strangely, even ice can behave like a liquid, not the brittle cracking ice we know from winter sidewalks or frozen lakes. but exotic ices, made of substances like methane, nitrogen, ammonia, and even carbon monoxide, can move across a landscape with a grace that defies our instincts. They can slide, deform, and slowly reshape a world over vast timescales. This is how ice flows like lava. On Pluto's Sputnik Planitia, nitrogen ice fills a broad, heart-shaped basin. It doesn't just sit still, it moves, very slowly. It convects in massive cells, pushing older ice down and bringing newer ice up in cycles that can last millions of years. There's no fire beneath this surface, just a quiet stirring, driven by the difference in temperature between surface and depth. Cold at the top, less cold deep below. Nitrogen ice is particularly good at this kind of slow motion. At Pluto's surface temperatures, around minus 230 degrees Celsius, it becomes soft over long periods. Imagine frozen butter that, given time, starts to slump under its own weight. That's what's happening across Sputnik Planitia, not in minutes, not even in years, but across epochs. Elsewhere in the solar system, ammonia plays a similar role. When mixed with water, ammonia lowers the freezing point of the mixture, creating a kind of antifreeze slush that may remain liquid even when everything else is solid. Some moons may be laced with this slush just beneath the surface. When pressure builds or a crack forms above, the mixture could escape and slowly ooze outward, freezing as it cools, forming low, broad domes or smooth plains. This is not the kind of eruption that builds mountains. It builds calmness, softly rising ground, rippled textures, thin layers of frozen history. One of the best places to see this kind of ice flow is on Neptune's moon Triton. There, the surface includes smooth areas that look as though something once welled up and spread outward. Not violently, but in a hush. Another example may be found on Saturn's moon Titan. Titan has a dense atmosphere and is rich in methane and ethane, compounds that, at Titan's temperatures, behave like water does on Earth. Lakes, rivers, even rain, all made of hydrocarbons. But beneath its crust, scientists believe a layer of water ammonia ice may exist, and in certain places, that ice may rise to the surface through cryovolcanic activity. Radar images from the Cassini mission revealed structures on Titan that could be ancient cryovolcanoes, like Sotra Patera, a deep depression surrounded by flow-like features. If these are real cryovolcanic structures, then Titan may be reshaping itself through slow oozes of icy lava. These flows, unlike lava on Earth, would be cold and dense. They might crawl across the surface over years or decades, eventually freezing solid into strange rounded formations. From above, they could look like pancakes, or smudges, or softly frozen waves, but their presence speaks volumes. Because ice, in these distant worlds, is not just a solid. It's a material that responds to gravity, to temperature, to pressure. It is dynamic, alive in a geological sense. This challenges our intuition. We grow up learning that ice is solid and unchanging, that flow requires heat, that motion implies fire. But in the solar system's outer realms, the rules shift. Here, cold can flow, stillness can move, solids can behave like liquids, given enough time and space. That's one of the beauties of planetary science. It reveals that nature is broader than our everyday experience, that the laws of physics apply everywhere, but their expressions vary across distance and temperature. Astrophysicists still study how different ices behave under pressure. In laboratories on Earth, they simulate the conditions of Pluto, of Triton, of Titan. They freeze ammonia water mixtures, compress nitrogen crystals, and watch as these substances deform, slowly but steadily, under the weight of time. Their findings help explain the rounded hills, the rippling basins, the smooth plains we see in distant spacecraft imagery. But much remains uncertain. How fast do these flows occur? What causes them to start and stop? Are they ongoing now, or are we seeing the preserved remnants of ancient motion? We don't yet know. But what we do know is this: ice is not always still. In the outer solar system, ice can rise and fall, spread and collapse, build and erode. It can carry the memory of hidden warmth. It can leave behind patterns that whisper of subsurface seas, quiet eruptions and slow, slushy tides. We may never stand on these distant worlds, but through images, through models, through the slow gathering of clues, we can imagine them. We can picture the flow, not rapid, not roaring, but steady and soft. A glacier of nitrogen sliding across a crater floor. A dome of ammonia-rich ice, rising like breath beneath a frozen sky. And somewhere, beneath it all, a warmth that refuses to fade completely. A quiet persistence that keeps the ice moving, shaping, dreaming. In the stillness of deep space, even cold can find its way forward. In a realm where sunlight is a faint flicker and heat is a memory from billions of years ago, what could possibly keep these distant moons warm enough to move, to flow, to breathe? The answer, it seems, is not a single source, but a quiet combination. A slow, steady layering of warmth from different places. Subtle, persistent, and often invisible. One of the most important of these is tidal heating. Unlike the heat we know on Earth, generated by sunlight or friction or chemical fire, tidal heating is quiet and rhythmic. It's the result of gravity playing tug-of-war with a moon's interior. Imagine a moon orbiting a massive planet, say Europa around Jupiter or Enceladus around Saturn. These orbits are rarely perfect circles. As the moon moves closer and farther from its host planet, gravity stretches and compresses it. This flexing creates internal friction. The rock and ice inside the moon rub together gently, over and over, producing heat. It's not much, not like the volcanic heat of Earth's mantle, but over time, this energy adds up. It can warm subsurface oceans, melt icy pockets, and even trigger cryovolcanic eruptions. Enceladus, for example, is so small that without tidal heating it would have frozen solid long ago. But Saturn's gravity pulls on it relentlessly, and this constant kneading keeps parts of its interior warm. It may be this very heat that fuels the water plumes we've seen erupting from its south pole. The same is likely true for Europa. Trapped in a gravitational dance with Jupiter and its fellow moons, Europa is squeezed just enough to keep a vast hidden ocean in liquid form beneath its icy shell. But tidal heating is not the only player. There is also radioactive decay. Even the coldest moons contain trace amounts of radioactive elements, uranium, thorium, potassium, locked inside their rocky cores. These elements decay over time, releasing energy. On Earth, this process helps drive plate tectonics and volcanic activity. On icy moons, the energy is weaker but still significant. Over billions of years, this internal heat can be enough to keep a subsurface ocean from freezing entirely, especially if the outer layers of ice act as insulation, trapping warmth deep within. Ceres, for instance, has no large planet nearby to create tidal flexing, but radioactive decay in its core may provide just enough warmth to keep briny pockets from freezing, allowing for the slow rise of salt and vapour to the surface. And then there's gravitational contraction. Some moons and dwarf planets may still be slowly settling into themselves, compacting over time as their interiors shift and reorganize. This movement releases energy, albeit faintly. It's a kind of leftover warmth from formation, still echoing faintly after billions of years. The heat from formation itself, the original collisions and compressions that built these bodies, has mostly dissipated. But a few places, particularly larger or denser moons, may retain echoes of this primordial heat buried far below the surface. All these processes are quiet. None would warm your hands if you stood nearby. But combined, they create a kind of hidden life, a geological murmur that sustains oceans, cracks crusts, and fuels the occasional breath of a cryovolcano. Even on Pluto, far beyond the reach of the sun's warmth, internal heat may be at work. There's no tidal force there, not like on Enceladus or Europa, but radioactive decay, combined with thick layers of insulating ice, could help explain features like Sputnik Planitia and the possible cryovolcanoes nearby. On Titan, tidal heating is less intense, but its dense atmosphere helps retain surface temperatures, allowing for the possibility of internal warmth rising slowly through its thick shell. Triton, caught in its unusual retrograde orbit, experiences strange tidal forces as well. Some scientists believe that its captured status may have set off waves of heating and cooling cycles that lasted for eons, maybe even long enough to sustain internal activity. But here's where the mystery deepens. Astrophysicists still debate how much heat is actually available inside these icy worlds. Measurements are difficult, models vary, and every moon has its own history, its own composition, its own dance of orbit and tilt and distance. Some moons, like Callisto, may have frozen solid. Others, like Ganymede, may retain deep oceans locked beneath miles of hard crust. And still others, like Enceladus and Europa, show signs that their internal warmth is more than just theoretical. But even for those that seem quiet now, there may be more beneath the surface. Perhaps their interiors are not entirely frozen. Perhaps slow pulses of heat still ripple through their cores. Perhaps vents open and close over geological timescales, breathing once every few million years. If so, we may only be seeing these moons during their silent phase. What matters is that warmth, even in tiny doses, can change everything. It can melt ice. It can move mountains. It can create oceans, and oceans in turn may host chemistry, currents, possibility. So when we look at these cold, quiet moons and wonder whether cryovolcanoes still breathe beneath their crusts, we're really asking a deeper question. Is warmth still alive, even here? Does the ancient fire still whisper beneath the frost? We don't need dramatic eruptions or glowing lava to say yes. A faint plume, a soft haze, a ripple in the ice. These are the signs. They tell us that heat can hide, that motion can be subtle, that life, geological or biological, might persist in places where silence reigns. Even in the cold, something moves. And perhaps somewhere something waits. In the stillness of deep space, where sunlight arrives as little more than a whisper, we rely on more than eyes to know what's unfolding on those distant, icy worlds. To detect the faint breath of a cryovolcano, we need other senses. Senses crafted by human hands and sent across billions of kilometers. Eyes made of metal and mirrors, instruments that watch without blinking. We begin with the watchers. Cassini, Galileo, New Horizons, Dawn. Names that sound like whispers themselves. Each of these spacecraft played a role in revealing the hidden lives of moons and minor planets, shedding light on what no human eye could ever see directly. Cassini was perhaps the most famous, lingering in the Saturnian system for more than a decade. It gave us not just the iconic plumes of Enceladus, but a deep and patient gaze. Over dozens of flybys, Cassini mapped the surface, measured thermal emissions, sampled icy spray, and listened to electromagnetic pulses. It wasn't one instrument that told the story, it was the chorus. The Imaging Science Subsystem, or ISS, captured plumes in backlight, letting faint mist show against the darkness. The Composite Infrared Spectrometer, or CIRS, detected warmth along the tiger stripes, regions that, against all expectations, weren't as cold as they should be. The Ion and Neutral Mass Spectrometer, or INMS, flew through vapor, tasting its chemistry in real time. Salts, water, organics. Each data point was quiet on its own, but together they whispered a truth. This moon breathes. Galileo, before Cassini, had orbited Jupiter and stared long and hard at Europa. Its instruments detected a magnetic signature, an induced field, suggesting a salty ocean beneath Europa's crust. The Near-Infrared Mapping Spectrometer, or NIMS, hinted at water ice interactions on the surface, and though Galileo never saw a plume, its data laid the foundation for what we now expect to find there. Then came New Horizons. Bound for Pluto, it raced through the Kuiper Belt with just one shot at a close pass. Its brief flyby in 2015 lasted only hours, but in that time it transformed Pluto from a pixel to a world. Its instruments revealed Sputnik Planitia, smooth, craterless, and moving. They detected ammonia-rich ices, methane haze, and curious mountains. Though it couldn't confirm active cryovolcanism, it found strong clues. Terrain too young, forms too strange. Evidence that something, sometime, had stirred. New Horizons carried LORRI, the Long-Range Reconnaissance Imager, which gave us our first clear view of Pluto's surface. It also carried instruments for mapping composition and temperature, like LISA and REX. These tools, working in harmony, offered a portrait of a complex, evolving world. And then there was Dawn. Dawn orbited Vesta, then Ceres. At Ceres it uncovered bright spots, those shining salt deposits in a Cater crater. Its framing camera, infrared spectrometer, and gamma-ray detector worked together to build a map of composition and structure. The Dawn team even reprogrammed the spacecraft to spiral closer for a better view of the central dome in Cerealia Facula. There too they found hints of recent activity. A surface not as cold as expected. Patterns of flow. Gentle slopes that suggest something once moved. But our tools aren't always spacecraft. Sometimes we watch from afar. The Hubble Space Telescope orbiting Earth has spotted what appear to be plumes above Europa. Faint arcs of water vapour, only visible against the backdrop of a distant star. Not confirmed, not sustained, but enough to keep us curious. Enough to justify a return. That return is coming. NASA's Europa Clipper, launching soon, will carry a suite of instruments designed to map the ice, sample any plume it can find, and listen for the subtle signs of a moon alive beneath its surface. There's also the JUICE mission, Jupiter Icy Moons Explorer, from the European Space Agency, on its way to Ganymede and Europa. It too will watch, will listen, will help us understand how and why these frozen worlds might stir. And the watching doesn't stop at the solar system's edge. We now use Earth-based observatories and orbital telescopes to detect heat signatures, albedo changes, and spectral fingerprints. Instruments like ALMA, the Atacama Large Millimeter Submillimeter Array, can detect the presence of gases in thin atmospheres, even from across the solar system. These are not dramatic tools. They don't thunder or flash, but they are precise, patient, designed to detect the barely there, the half-seen shimmer of vapour, the ghostly warmth of a fractured plane. Astrophysicists still debate what constitutes proof. A thermal anomaly could be an instrument artifact. A dark streak might be a landslide, not a plume. A haze might be sublimation, not eruption. We move forward by consensus, by careful layering of evidence. The truth reveals itself slowly, but in every case, whether we find definitive cryovolcanoes or not, our instruments help us learn. They help us see a cosmos that is not static, a solar system not frozen, a set of moons not dead. Our eyes, extended through technology, are beginning to catch up with our wonder. And wonder, after all, is the reason we build these machines. Because we want to know, is anything still breathing out there? Is that silence truly silence? Or just a sigh too soft for our ears? Beneath layers of ice, in places we'll likely never touch with our hands, lie oceans hidden in shadow. These seas have no winds, no tides pulled by a moon, no sunlight to warm their surface, and yet they may be the most dynamic, active places in the solar system. They whisper upward, slowly and softly. On moons like Europa, Enceladus, and perhaps even Titan and Pluto, vast liquid oceans are believed to lie beneath their frozen exteriors. These oceans are not imagined, they're inferred, detected by the subtle fingerprints they leave on the world above, a shifting crust, a magnetic signal, a geyser caught in silhouette. But how could an ocean trapped beneath kilometres of ice ever make itself known? That's the quiet miracle of cryovolcanism. It offers a path. If a subsurface ocean is under pressure, pressing against an icy shell, it may find a way to escape. Not in a roar, but in a hush. Through cracks, fissures, or thinned regions of crust, the ocean may rise. It may not reach the surface directly. The passage might be slow, interrupted, diverted. The water might freeze along the way or turn into vapour, but some of it, if the conditions are just right, can make the journey. And when it does, it carries a message. A molecule of salt. A fragment of organic material, a trace of ammonia. These may ride upward on vapour, released from a vent, and drift into the cold. They may land again as frost, or spiral outward into space. This is how an ocean speaks. On Enceladus, we've seen it clearly. Cassini flew through those plumes, jets of water vapour shooting from the South Pole, and detected not just water, but complex organics. Not life, but possibility. The very idea that ocean material had found its way through 30 or 40 kilometres of ice to escape into space was astonishing. It changed our perspective, because it meant we didn't need to drill. The ocean was reaching out to us. Europa may be doing something similar. Hubble's hints of vapour plumes above the moon's south pole suggest that, at times, water from the ocean below may breach the surface. It might not be as consistent or dramatic as Enceladus, but even occasional plumes could allow us to sample the ocean indirectly. Astrophysicists still debate the mechanics. How does water make that journey? Is it forced upward by pressure? Is it drawn along fractures by expanding ice? Are there chambers that fill and burst like geysers on Earth? No single answer fits all moons. On Titan, things may work differently. Its icy shell is likely much thicker than Enceladus's, and the ocean beneath might be layered with ammonia-rich slush or silicate sediments. Cryovolcanism here may take the form of oozing domes or subsurface upwellings that never quite break through. Still, surface features like Sotra Patera suggest that something has moved. Something has tried to speak. The importance of these oceans cannot be overstated, not just because they move, but because they may host chemistry. Water, when in contact with rock, creates opportunities. Hydrothermal vents, dissolved minerals, energy gradients. On Earth, these conditions are teeming with microbial life. Bacteria that eat sulfur, archaea that thrive in boiling acid, life that doesn't need light, only the right molecules in the right places. Could the same be true on Europa or Enceladus? We don't know, but the presence of a path from ocean to space is a starting point. We can imagine it now, a molecule formed deep in the ocean, drifting upward in darkness, carried through a narrow fracture, evaporating into a plume, and eventually caught in the instrument bay of a passing spacecraft. One journey, billions of years in the making. This is why future missions matter. Europa Clipper will fly past Europa dozens of times, scanning the surface, looking for plumes, testing the ice. If it finds even a whisper of ocean material escaping, it may help us understand not just the moon's structure, but its chemistry. A future lander, perhaps even a sample return, could follow, a spacecraft designed to taste the frost, to scrape the surface where plumes once fell, and search for the signatures of life, not proof necessarily, but signs. And signs are where stories begin. Meanwhile, theoretical work continues. Scientists build models of how briny water behaves under pressure, how fractures form, how ice cracks. They simulate plume formation, molecule survival, and the potential biosignatures we might detect. They are learning to listen, because subsurface oceans don't speak in words. They speak in minerals, in salts, in movement. They breathe through their ice, slowly, quietly, and perhaps persistently. Even if cryovolcanism is rare, even if only a few vents remain active, even if the oceans are calm, the fact that they are there at all is extraordinary. Beneath the silence of Europa's ice, a sea still sloshes. Beneath Enceladus, a briny tide presses upward, and perhaps, beneath other frozen worlds, oceans wait their turn, to move, to rise. To whisper upward through the crust, to remind us that even in darkness something still stirs. If a cryovolcano erupts in the outer solar system, how would we even know? There is no sound in space, no glowing lava to draw the eye from afar, no thunder, no smoke, no shaking ground beneath our feet. These frozen eruptions speak in subtler tones, in invisible vapour, in shifting light, in spectral traces left in the cold. And to catch them, we must learn to see the unseeable. This is the science of faint plumes. When Cassini first spotted geysers on Enceladus, they weren't obvious. The spacecraft had to position itself carefully, letting sunlight backlight the moon so that any rising vapour could silhouette against the blackness. In normal lighting, the plumes were nearly invisible, just a hint of mist, a whisper of a trace. But once the geometry was right, there they were. Dozens of jets fanning outward in gentle arcs from the South Pole, reaching tens or hundreds of kilometres high. Silent fountains drifting into space. On Earth we track volcanoes with seismographs and thermal cameras, but on icy moons we use different tools. Plume detection starts with light, especially the invisible kinds. Ultraviolet imaging can pick up water vapour, which absorbs certain wavelengths. Instruments tuned to these frequencies can detect the shadow of a plume as it passes in front of a star or a planet. This is called stellar occultation. The object is backlit, and the plume leaves a fingerprint as it drifts by. Infrared spectrometry is another key. Warmth is rare on these worlds, so any localized thermal anomaly stands out. A region just a few degrees warmer than its surroundings can be flagged as unusual. That's how Cassini found the tiger stripes, warm fissures suggesting recent or ongoing activity. Mass spectrometers too can detect faint plumes, if the spacecraft flies directly through one. They measure the composition of particles and gases in real time, distinguishing between water, ammonia, methane, and other molecules. And then there are the subtle signatures, changes in surface brightness, a new frost deposit, an alteration in chemical reflectivity. These are clues that something may have erupted recently, even if the plume itself has vanished. New Horizons, for instance, saw no active plumes on Pluto, but the terrain hinted at the possibility. Some craters looked as though they had been filled or smoothed. Some mountains rose like old cryovolcanoes worn down by time, and the surrounding plains showed signs of upwelling, patterns that may point to past eruptions. We're also learning to look sideways, to compare, to contrast. Enceladus shows bright, narrow fissures. Europa shows broader ridges and chaos terrain. Triton has long, dark streaks trailing downwind. Each of these features hints at motion, release, escape. Each might be a cryovolcanic fingerprint, but interpreting those fingerprints requires care. Astrophysicists still debate what we're seeing. A dark streak might be from a plume, or from surface winds. A bright patch could be fresh frost, or just a lucky angle of sunlight. A smooth plain might be cryovolcanic, or just unusually young. This is where patience comes in. The science of faint plumes is built on repetition, multiple flybys, layered data sets, return missions. We watch over time, building confidence, refining models, and slowly converging on the truth. Europa Clipper, when it arrives, will help immensely. It will carry an ultraviolet spectrometer, Europa UVS, designed specifically to catch plumes in the act. It will scan for hydrogen and oxygen, break down products of water vapour. It will track temperature variations with a thermal imager and probe surface chemistry with spectrometers. The goal isn't just to confirm a plume, but to characterise it. How tall is it? What is it made of? How fast is it moving? How often does it erupt? By answering these, we can learn more about the source. Is the water coming directly from an ocean or from a shallower pocket? Are there salts? Organics? Could the material have passed through regions warm enough for life? Plume science is about connection, connecting what we see in space to what we suspect beneath. And it's not just about what's erupting now. Some moons may be in a quiet phase. Their cryovolcanism could be episodic, tied to orbital cycles or internal pressures that build and fade. A plume may only occur once in a decade or a century. But the signs of past activity may still be visible. By studying surface patterns like fissures, ridges and deposits, we can estimate how often such activity might occur. We can model the physics of ice cracking, the buoyancy of brine, the pressure needed to lift a plume into the vacuum of space, and we can prepare, so that when the moment comes, when a spacecraft is in the right place at the right time, we're ready to catch the breath. Even now, new instruments are being developed. Telescopes tuned to sub-millimeter wavelengths, CubeSats designed to orbit icy moons, landers that may one day rest directly on a tiger stripe or chaos plane, because the more we listen, the better we hear. And what we're hearing, faint though it is that silence is not the absence of motion. It is just the edge of our detection. Beyond it, plumes may still rise, cryovolcanoes may still sigh, oceans may still reach upward, molecule by molecule trying to tell their story. We're learning their language, a language of frost, of vapour, of warmth in cold places, a language of plumes. Sometimes the signs of cryovolcanism are hidden. No plumes, no geysers, no fresh frost glinting in starlight, just cold silence, a surface still and bare. But even here, we keep looking. Because even when there's no visible breath, there may still be warmth. No smoke, still fire. It's a quiet principle that guides planetary scientists as they study distant icy worlds. In the absence of active eruptions, they turn their focus to thermal anomalies, places that are just a bit warmer than they should be. Not hot, not glowing, just less cold. On a world like Enceladus, where surface temperatures average around minus 200 degrees Celsius, an area that's 5 or 10 degrees warmer stands out. That slight difference could mean something is happening beneath, something stirring, something moving. This was exactly what Cassini found. The south pole of Enceladus, home to its iconic tiger stripes, wasn't just geologically interesting, it was thermally unusual. Cassini's instruments detected heat emissions that couldn't be explained by sunlight alone. The fissures were warm, and the warmth was sustained over time. The plumes, it turned out, weren't isolated jets. They came from these warm cracks. The ice around them was softer, more pliable. This allowed water to escape in a slow, controlled exhale. And even when the plumes weren't visible, the warmth remained. That's what made the difference. The warmth itself was a sign. Thermal imaging has since become one of the most valuable tools in the study of cryovolcanism. It can reveal the faint signature of heat escaping from a vent, a dome, a fracture. It can hint at subsurface oceans close to the surface. It can help distinguish between a static plane and one that's quietly shifting beneath a veneer of frost. On Europa, upcoming missions will carry thermal images specifically for this reason. If a patch of ice is slightly warmer than expected, it might be a sign of a recent eruption, or one about to come. Or perhaps it's just a lingering fingerprint from something long past. Either way, it tells us that something is different. Pluto's case is similar. During New Horizons flyby, the spacecraft measured temperatures across the dwarf planet's surface. Sputnik Planitia, the vast nitrogen ice basin, showed signs of convective movement. No visible plumes, no warmth obvious to the eye, but hints of thermal activity beneath. Slowly churning ice, gently shifting patterns. These aren't the marks of dramatic eruptions, they are the marks of quiet motion. Astrophysicists still debate the thresholds. How warm is warm enough to indicate cryovolcanism? What else could be causing the heat? Could surface composition or sunlight angle be fooling our instruments? The caution is warranted. A dark patch of methane ice may absorb more sunlight than surrounding water ice, creating the illusion of warmth. A surface smoothed by sublimation may look young, even if it's ancient. But when warmth is paired with other features, fractures, domes, unusual chemistry, it becomes a stronger clue. A Hunamons on Ceres is one such clue. It doesn't emit heat now, but its shape, lack of craters, and isolation suggest it formed relatively recently. Perhaps from a single, slow eruption of salty slush that crept upward and froze into a dome. No smoke, still fire, and on moons like Titan, where a dense atmosphere complicates remote sensing, thermal data becomes even more valuable. Instruments can see through the haze, detect temperature gradients, and find places where warmth leaks gently from below. The signs are often faint, a fraction of a degree, a tiny shift, but in the cold of the outer solar system, even a small rise in temperature can carry enormous meaning, because warmth is precious out there. It doesn't linger without reason. It has to come from somewhere. And when we find it, we pause, we wonder, we listen. Could this be a cryovolcano in its quiet phase? Could this be a vent that's not erupting now, but did in the recent past, or will again? These are the kinds of questions that guide future exploration. They help us decide where to send landers, where to scan more deeply, where to listen more closely. Some thermal anomalies fade with time, others stay put. Some shift across seasons, responding to orbital changes or subtle tectonic stress. We've even seen rhythmic patterns. On Enceladus, the heat output from its tiger stripes appears to vary slightly over time, possibly tied to its orbit. This suggests that cryovolcanism might not be constant but cyclical, pulsing with the tides, breathing in and out across decades or centuries. It's a beautiful thought that somewhere out there, beneath a crust of ice, a sea is stirring, not erupting wildly, but pressing gently upward, leaking warmth, sending signals we can only detect with the most sensitive instruments. And when we find those signals, those faint glimmers of heat, we are reminded of something deep and simple, that stillness is not the same as silence. That a world can be quiet but alive, that a cryovolcano, even when it does not erupt, still matters, because its warmth is a message, its breath, even unspoken, tells us a story of pressure, chemistry, and time. No smoke, still fire. And in that fire, faint as it is, lies the story of motion in the deep. Beneath every shimmering image of a distant moon, beneath every glint of ice or trace of vapour, lies another layer entirely. Not just data, but interpretation. And interpretation, like the icy surfaces we study, can shift with time. In the study of cryovolcanoes, not all scientists agree. Not every feature is seen the same way. Where one sees evidence of eruption, another sees tectonics. Where one sees a plume, another sees sublimation or surface weathering. The whisper of an icy breath becomes a matter of debate. This is the quiet tension beneath our growing understanding. Astrophysicists still debate whether the features we see, dome-shaped mounds, smooth plains, fractured crusts, are truly the fingerprints of cryovolcanism, or whether they may be shaped by other processes entirely. Take Pluto, for instance. The vast domes of Wright Mons and Picard Mons suggest possible cryovolcanic origins. Their shape is irregular but distinct. Their surfaces are relatively uncratered. Their surroundings hint at slow flows, but they lack obvious vents, no signs of recent eruption, no plumes. and so some researchers suggest they may be tectonic in origin, uplifted by internal pressure rather than built by extrusion. Ceres presents another puzzle. The bright salt deposits in Ocata crater clearly came from within, but did they rise from a true cryovolcano or simply seep through cracks as brine? The crater itself was formed by impact. Could that alone have triggered the upwelling? And Europa, its surface is a patchwork of ridges, blocks and chaos terrain. The patterns suggest movement, something beneath, but is it cryovolcanism, or the result of flexing ice plates grinding against each other? We ask these questions not because we doubt the science, but because science thrives on doubt. Interpretation in planetary geology is shaped by comparisons. On Earth, we know what a lava dome looks like. We understand the cooling of magma, the spreading of basalt. But when we peer at a world with no atmosphere, no sunlight, and an entirely different chemistry, the analogues break down. Ice is not rock. Ammonia is not water. A plume of nitrogen behaves differently from a plume of ash. And so, every cryovolcanic hypothesis becomes a quiet conversation. Some scientists point to modelling. Simulations show that internal pressures could cause icy eruptions. Thermal gradients, tidal flexing, and chemical buoyancy all support the idea. Others point to observational gaps, features that resemble volcanism but could just as easily be shaped by erosion, impact, or sublimation. There's also the matter of timescale. On Earth, we can study volcanic activity over years or decades. On icy moons, we get snapshots, brief flybys, limited images, low-resolution scans. We rarely get to watch these surfaces change, and so much of what we know is frozen in time. What looks like a cryovolcano may be ancient, or young, or misunderstood. Even on Enceladus, where active plumes have been seen with our own instruments, debate persists. Are the plumes from a global ocean? Or from isolated pockets of liquid? Do they indicate life-friendly environments, or just cold mechanics? Different missions return different clues. Each set of instruments comes with its own strengths, its own limitations, and interpretation often depends on how those pieces fit together. But in the midst of all this uncertainty, something beautiful happens. The conversation deepens. Disagreement doesn't silence the search, it expands it. It invites new missions, new models, new methods. It pushes researchers to ask better questions, to refine their tools, to design instruments that can pierce the ambiguity. This is how we move forward. Already, future missions to Europa and Enceladus are designed with these uncertainties in mind. Thermal imagers will look for subtle warmth. Radar sounders will map the structure beneath the crust. Mass spectrometers will seek the molecules that could distinguish venting from surface weathering. And with each pass, each sample, each pixel sharpened, the debate will evolve. Perhaps we will confirm more cryovolcanoes, soft eruptions caught in real time, or perhaps we'll redefine what it means to erupt. Perhaps we'll discover that ice tectonics and cryovolcanism are not separate categories, but part of the same spectrum, a quiet continuum of motion beneath the frost. Even now, some scientists propose that cryovolcanism may not be a distinct process at all, that it may be just one expression of internal activity, a venting phase in a longer, slower cycle of crustal flexing, brine migration, and surface renewal. That idea that cryovolcanism is not a singular act, but part of a larger conversation between heat and ice, pressure and chemistry, is quietly transformative. It invites us to think in longer rhythms, to read the surfaces of moons not as frozen facts, but as evolving poems. Each ridge, each fracture, each dome may be a line in that poem, a verse about a time when the interior spoke, not loudly, not definitively, but sincerely. And so, even when scientists disagree, even when theories diverge, the shared goal remains: to listen more carefully, to see more clearly, to understand more fully. Because somewhere out there, beneath the silence, something is still moving, still expressing, still becoming. And whether we call it cryovolcanism, tectonics, or something we haven't yet named, we are all listening together. In all the drifting vapour, the cracked ice, the warmth beneath frost, one question hangs in the stillness like a thread waiting to be pulled. Could something be alive down there? It's not a question we ask loudly. It's not a declaration. It's a whisper, a wonder, a thought that flickers across the minds of those who study these distant moons and frozen oceans. Because when we speak of cryovolcanoes, of vents that breathe, of plumes that rise, we are not only speaking of geology, we are speaking of access, of possibility, of a bridge between surface and sea, and in those seas perhaps the conditions are just right, not perfect. Not comfortable by Earth standards, but right enough for life. At the bottom of Earth's oceans, in places where sunlight never touches, life thrives. Entire ecosystems exist around hydrothermal vents, creatures nourished not by light but by heat and chemistry. Tube worms, microbes, crustaceans, all feeding on mineral-rich fluids rising from the planet's deep interior. These environments are dark, cold and extreme, and yet they are teeming. So when we find oceans beneath Europa or Enceladus, warmed not by the sun but by the slow kneading of gravity or the decay of ancient atoms, we can't help but wonder, could something similar exist there too? Enceladus is the most compelling example. Its plumes don't just carry water vapour. Cassini detected molecular hydrogen, a potential energy source for microbial life. On Earth, similar hydrogen-rich vents host thriving ecosystems. The presence of hydrogen suggests water rock interactions, possibly hydrothermal activity on the ocean floor, warmth and minerals mixing, chemistry happening. Astrophysicists still debate how extensive this process might be. Is the ocean deep and globally connected? Are the vents localized or widespread? Does the ocean have a rocky floor, or is it suspended above layers of thick insulating ice? We don't yet know. But what we do know is enough to spark quiet, cautious excitement. Because where hydrogen flows and water remains liquid and organics exist, as Cassini found, there is potential, not certainty, not expectation, but possibility. Europa tells a similar story, though with fewer data. Hubble's hints of water vapour plumes suggest that ocean material might reach the surface. Europa's magnetic field implies a salty ocean in contact with rock. Surface features, like chaos terrain, hint at ice shifting from below. If Europa's ocean interacts with rock, and if organics are present, it could offer the same basic ingredients: water, energy, carbon chemistry. Titan too may host life, though of a very different kind. Its surface lakes and rivers are made not of water, but of liquid methane and ethane. Some scientists speculate about life that uses methane as a solvent, a truly alien biochemistry. Beneath Titan's crust, a water ammonia ocean may lurk. There, perhaps, more familiar life could stir. Even Ceres enters the conversation. Though it's smaller and lacks a global ocean, its briny pockets and possible cryovolcanism make it a quiet candidate. Salts, water, heat. The basic recipe is there, though whether it ever cooked into life remains unknown. Of course, none of these places offer a direct view. We haven't seen a cell. We haven't heard a heartbeat, but the ingredients are lining up, and cryovolcanoes, these soft, icy exhalations, may be the link, because without them, these oceans remain sealed away, inaccessible. With them, we have a path, a way to sample ocean chemistry, to catch a molecule in flight, to examine what's rising from the deep. A single plume rising from the cracks of Enceladus could carry more than mist. It could carry amino acids, complex organics. Perhaps even the detritus of tiny life, cells long since expired floating upward through the cold. It's a long shot, a quiet hope, but one worth following. Already mission plans are forming. Europa Clipper won't land, but it will sniff, sample, analyse. If it finds signs of life-friendly chemistry in a plume, it may be the first step toward a more focused search. A future mission to Enceladus, sometimes imagined as a sample return or even a lander, could go further, collecting fresh plume material and analysing it on site, not for ambiguous markers, but for biology itself. Still, we tread carefully. Because the line between organic chemistry and life is thin and fragile and easy to misread. Methane, for example, can be produced by microbes or by rock reacting with water. Amino acids can form in space, on asteroids, without life. Salt, heat and liquid water are necessary but not sufficient. Astrobiologists know this. They speak softly. They wait for patterns. They look for combinations of factors, molecules that occur together, or in specific ratios that life tends to prefer. They search for anomalies, unlikely chemistry, disequilibrium, not because they expect to find it, but because they are open to being surprised. And if that surprise ever comes, it will change not just our understanding of cryovolcanism, it will change our understanding of ourselves. To know that we're not alone, that life can arise more than once, that biology is not a fluke, but a possibility woven into the cosmos. That would be a quiet, profound truth. Not shouted, not sensational, just real. A whisper that began as a plume of vapour, a sigh rising from beneath the ice, a breath from a moon adrift in starlight. Perhaps even now a single microbe floats in a salty sea beneath Europa's crust. Perhaps it drifts near a vent, feeding on minerals, unaware of us, unaware of itself. Perhaps someday we'll meet. If cryovolcanoes are alive today, they're likely not always so. Like the breath of sleeping giants, their activity may come and go, not in bursts, but in long, deep rhythms, the kind measured not in days or years, but in millions of orbits around the sun. We often imagine volcanic eruptions as sudden, urgent things, lava racing down a slope, fire lighting the sky. But cryovolcanism in the outer solar system does not move like that. It's not a roar, but a rhythm, a cycle, a patient rise and fall of pressure and warmth, shifting like tides beneath an icy crust. And these rhythms might leave behind patterns we can read if we look slowly enough. On Enceladus, for instance, the tiger stripes at the South Pole may not erupt continuously. Observations from Cassini suggest that the plumes intensify at certain points in the moon's orbit, then wane. It's a tidal rhythm, gravity flexing the crust, opening and closing fissures, a breath in, a breath out. But over longer timescales, the entire system may pulse in ways we don't yet fully understand. Ocean pressures may rise and fall, ice shells may thicken or thin, vent systems may clog, freeze, reopen. Some epochs might be quiet, others might be restless. Europa too shows signs of episodic behaviour. The chaos terrain, the strange regions where ice seems broken and reassembled, may have formed during periods of intense geological activity. Perhaps the crust softened from below, melted and then refroze. Perhaps the ocean pushed upward in certain ages only to retreat in others. Cryovolcanism could be part of this rhythm, not constant process but one that flares up when conditions align. Internal heat, thin crust, fractured paths to the surface. Even Pluto, despite its frigid distance, may follow such a cycle. Its smooth plains and cryovolcanic domes may not be erupting now. But they look young, geologically young. Features like Wright Mons and Picard Mons may have formed within the last few 100 million years. A blink in Pluto's 4.5 billion year history. Did they erupt once and freeze? Or do they pulse slowly, releasing icy material every few million years? We don't know. But the lack of craters on their surfaces suggests that whatever formed them happened recently, and that cryovolcanism there might not be entirely extinct. Astrophysicists still debate the cadence of such activity. Is it tied to internal decay of radioactive materials, to the stress of orbital resonances, to impacts that briefly crack the crust? Or are we seeing the end of the cycle, a final breath, captured just before the frost closes over? It's possible that some moons are caught in a fading echo, that they once erupted frequently but now only stir occasionally. Others may just be waking, or between breaths, and yet others may pulse with such long periodicity that we can't yet see the pattern. A plume that erupts once every 10,000 years would easily be missed by our brief visits. A dome that grows a few centimetres each century would seem static to the eye. We need patience and long vision. That's why future missions will watch over time. Europa Clipper, for example, will perform dozens of flybys across several years. It's not just looking for a plume, it's watching for patterns, variability, rhythms. Other missions may linger longer still. Orbiters, landers, perhaps someday even ice-penetrating probes that can listen for the creaks and sighs of shifting ice from within. Because geology is rarely a snapshot. It is music. Slow, cold music, playing through layers of rock and time. And cryovolcanism is one of its softest notes. There's something deeply poetic about this, that moons might breathe in cycles. That the silence we see now might be just a pause, that the signs we search for, plumes, warmth, fractures, might come again. Imagine a world where cryovolcanoes erupt not with urgency, but with elegance, a slow swelling, a release of vapour, a 1,000-year exhale. Imagine standing on the edge of such a place, beside a frozen dome under a star-filled sky, wondering if what lies beneath is stirring now, or will stir in a century, or already did, long before any eye could see. Cryovolcanism doesn't need to be constant to be meaningful. Its rhythm is part of the story, because even a breath taken once every million years is still a breath. Even an eruption that comes and goes over epochs leaves behind a message. We're learning to read those messages now, in crater counts, in heat maps, in the soft layering of ice across fractures, in the strange smoothness of alien plains. They tell us that time itself is a factor in cryovolcanism. Not just temperature or chemistry, but deep time, long winters, long silences, long awakenings. And that perhaps is part of what draws us in. Because in the quiet rhythm of these icy worlds, we see a reflection of our own long curiosity, our desire to understand things that move slowly, that change without haste, that breathe across the eons. Cryovolcanoes remind us that motion does not always roar. Sometimes it waits, and waiting is still living. To know whether a cryovolcano still breathes today, we must become gentle detectives of time, and one of the most reliable clues across the solar system is surface age. Not age in years, at least not directly, but age in craters. Because in a cosmos full of dust and debris, time leaves its mark not as wrinkles but as impacts. The longer a surface sits undisturbed, the more it accumulates scars. Craters bloom and stay. So when we find a smooth, unblemished region on a distant moon, our attention sharpens. Something must have erased the record. Maybe an impact melted the surface, maybe frost or wind filled the craters over time. But maybe, just maybe, something from beneath rose up, smoothed things over, made the old new again. And this is where cryovolcanism quietly enters the conversation. On Pluto, Sputnik Planitia is almost entirely free of craters. Its surface appears to be less than 10 million years old, possibly much younger. The ice there is not rock hard but mobile. Nitrogen and methane ices, under Pluto's weak gravity and low temperatures, flow slowly across the basin, renewing the landscape like a frozen ocean with no tides. It's not necessarily erupting from below, but it's definitely moving. To the west of Sputnik Planitia, Wright Mons and Picard Mons rise from the surface like soft eroded mountains. Their relative smoothness and lack of craters suggest they too are young, geologically speaking, maybe a few 100 million years old, maybe even less. That's recent enough to wonder if cryovolcanism on Pluto is still active today. Not everywhere, not always. But perhaps somewhere beneath that cold crust there's still a pocket of slush waiting to exhale. A quiet vent, a slow, icy bloom. On Series 2, crater counting has changed what we thought we knew. Ahuna Mons, possibly a cryovolcano, is remarkably smooth. Almost no impact craters dot its flanks. And that suggests it formed recently, maybe only a few 100 million years ago. In planetary geology, that's practically yesterday. Elsewhere on Ceres, the bright spots in a Cater crater also suggest youth. Their reflectivity implies freshness, salt deposits that haven't had time to darken or erode. And though we haven't seen them change with our eyes, their appearance hints that something happened not so long ago. Even Enceladus, whose plumes have been directly observed, has surface areas that help us track the rhythm of activity. The South Pole, where the tiger stripes vent water vapour into space, is smooth and clean. Not because it's young in age, but because it's being renewed, constantly. The particles ejected into space don't all escape. Some fall back as snow, others coat the surrounding terrain in a fresh layer of frost. This continual resurfacing leaves fewer craters, and that tells us something is active here, now. In contrast, the North Pole of Enceladus is heavily cratered, ancient, untouched. It's a quiet comparison, a reminder that activity is not uniform. Some places breathe, others sleep. Crater counting is one of the few tools we have that works across worlds. It's simple in concept, but profound in meaning. By comparing surface regions, those heavily cratered versus those clean and smooth, we begin to build a map of geological age. Astrophysicists still debate the exact ages, of course. Impactor rates vary across the solar system. Some moons are shielded by planetary magnetospheres, others lie in denser belts of debris. But the relative youth of some cryovolcanic features is undeniable. Triton offers a strange example. Its cantaloupe terrain, rounded, pitted, softly rolling, has very few craters. Voyager 2 revealed it to be one of the youngest surfaces in the outer solar system, yet we haven't seen it change since 1989. Does that mean Triton is quiet now? Or are its eruptions so slow, so rare, that we simply missed them? Perhaps we need to look at surface motion in a different way, not as eruption, but as renewal, not fire and flow, but uplift and smoothing. Because cryovolcanoes don't always erupt like fire volcanoes. Sometimes they swell, they seep, they push the crust upward gently, like dough beneath a towel. This is why elevation maps are useful too. By combining crater counts with topographic scans, we can find places where material appears to have welled up from below. A dome with few craters suggests recent activity. A plain with a strange, central bulge might mark a vent. Still, the question remains, how recent is recent? Some features may look fresh but be dormant. Others may look old but still breathe. So we study not just the craters, but their shapes. Are they sharp-edged or softened by frost? Are they partially buried by new material? Are they clustered in ways that suggest resurfacing? Each of these details helps narrow the timeline, helps tell us whether a cryovolcano last erupted 1 million years ago, or 1,000, because in the end, time is the quiet key. Cryovolcanism, like memory, fades into the surface unless renewed, and when it is renewed, by heat, by motion, by chance, it leaves behind a surface we can read, not like a book, but like a palimpsest, a layered script written across ice and silence. And if we read carefully enough, count patiently enough, we may begin to hear a story, that something moved here, not long ago, that something stirred and might stir again. Sometimes we learn about hidden things not by what they reveal, but by how they pull, by how they move the world around them. That's how we begin to listen through gravity's touch. Even if a cryovolcano doesn't erupt, even if no plume rises and no warmth escapes, something beneath the surface still exerts a presence. Oceans slosh, crusts flex, mass shifts quietly in the dark, and gravity, ever watchful, takes note. In planetary science, this is one of our subtlest tools. By measuring how a spacecraft is tugged ever so slightly as it flies past a moon, we can begin to map what lies beneath. It's like listening for a heartbeat, not through sound, but through the tiniest change in the pull of a world. This is how we've discovered subsurface oceans, not by sight, not by temperature, but by gravity. Europa's case is a landmark example. The Galileo spacecraft orbited Jupiter for years in the late 1990s. As it passed near Europa again and again, scientists noticed something odd. The moon's gravitational field shifted in ways that suggested a sloshy interior. Not solid rock, not stiff ice, but something that moved. More than that, Europa exhibited an induced magnetic field, a secondary field responding to Jupiter's strong magnetosphere. This could only be explained if something electrically conductive lay beneath the ice. A salty ocean, and not just a puddle or a sea, but a global ocean, possibly tens of kilometers deep, locked beneath a rigid shell of ice. Europa's gravity told us it was there, long before we imagined sampling it directly. The same technique has been used on Ganymede, Titan, and even Ceres. Small deviations in trajectory, minute delays in signal, all whispering of inner structures not seen but deeply felt. Enceladus gave us another clue. Cassini, during its flybys, noticed that the moon wobbled slightly more than expected, like a bell with a sloshing core. This wobble, called libration, suggested that Enceladus's outer crust was decoupled from the core, floating slightly on a subsurface sea. Even without the plumes we saw there, gravity alone would have told us something strange was happening. Gravitational mapping is especially powerful when paired with topography. If a surface bulge aligns with a gravitational high, we may be looking at a buried dome, possibly an upwelling of warm ice or a cryovolcanic mound. If a depression coincides with a low, it might be a collapsed vent or a drained chamber, and over time, changes in these signals could even hint at motion. No spacecraft has yet remained long enough at a cryovolcanic moon to map these shifts in detail, but missions like Europa Clipper and the proposed Enceladus Orbilander aim to do exactly that. By combining gravity, magnetism and radar, they'll peer beneath the crust without drilling a single hole. Like feeling for tides beneath a frozen pond, astrophysicists still debate what these measurements reveal. Is a gravity anomaly evidence of an active vent, or just a remnant of a frozen plume? Does a magnetic signal always imply liquid water? Or could certain mineral deposits mimic that behaviour? Interpretation is delicate, but even conservative estimates point to dynamism. These are not inert snowballs. They are layered, structured and responsive. Sometimes gravity shows us where an ocean is deepest. Sometimes it reveals where the crust is thinnest. Sometimes it catches a wobble, a planetary sigh, a hint that something inside is shifting with time. One elegant example comes from Triton. Its dense atmosphere made visual study difficult, but Cassini's radar and gravity instruments painted a picture, a thick, icy shell, beneath which likely lies a vast water-ammonia ocean. And beneath that, possibly a core of rock, warm, slightly active, pulling and pushing. The entire moon breathes, not through vents, but through tides. As it orbits Saturn, Titan stretches and relaxes, not dramatically, but enough to create internal friction, enough to keep its interior quietly stirred. Could cryovolcanoes ride those tides? Could domes rise and fall over eons, shaped by forces we measure only in fractions? Perhaps. Even now, models are being refined. New missions are being designed with gravity mapping in mind. instruments can now track the tiniest changes in velocity. A spacecraft speeding up by 1 millimeter per second? That's enough to suggest a hidden mass. In the future, multiple spacecraft could work together, trading signals, triangulating their paths, to build detailed maps of subsurface structures. And if we see a cryovolcanic dome with a gravitational bulge beneath it, or a vent site with a fluctuating signature across seasons, we may be watching a cryovolcano in the act of forming. Not erupting necessarily, just forming, pressing upward, shifting the mass, sending ripples through the world's quiet gravity field. This is the poetry of planetary science. Listening for motion through invisible pulls, feeling the weight of oceans we cannot see, watching ice rise not with light but with presence. Because even if a world is dark and quiet, gravity remains its voice. And if we tune ourselves just right, we can hear that voice whispering, something beneath is stirring, something beneath is rising, not in sound, not in light, but in the slow, soft rhythm of a world that still breathes. We've wandered far now, past Enceladus and Europa, beyond Pluto and Ceres, through plumes and plains and ice that flows like syrup in the cold. And yet, it's worth stepping back for a moment to ask why we listen so carefully, why we care whether cryovolcanoes still breathe. What do these quiet eruptions mean for us? They don't threaten cities, they don't shape climates, they don't even glow in the night sky, but they matter deeply because cryovolcanoes are messages from inside out. They tell us that the frozen surfaces of these distant worlds are not dead, that somewhere beneath the stillness, warmth still lingers. That pressure still builds, that change still happens, and that means something fundamental. The story of a world is still being written. In planetary science, this changes everything. When we see a surface cratered and unchanged, we assume it's a fossil, a remnant of ancient time, long since settled into silence. But a cryovolcanic feature shifts that assumption. It says, look again. The past may still be speaking. The interior may still be alive. That has profound implications for how we understand the evolution of icy bodies. It means they aren't just passive frozen objects. They're complex systems, layered, dynamic, and perhaps even interactive. Internal heat, chemical reactions, structural tension, all of these shape the landscape we observe, not just in the distant past, but possibly now. And these processes can inform us about Earth too. Our planet has a molten mantle and active plate tectonics, but Earth's water and its early organics may have originated from icy bodies, comets, asteroids, and perhaps even cryovolcanically active moons that once roamed differently through the solar system. Understanding cryovolcanism helps us understand how water moves through the cosmos, how heat persists in unlikely places, how materials mix, rise, and transform, and how geological activity can take on forms so different from our own experience, yet governed by the same quiet physics. But cryovolcanoes also nudge at deeper questions about life, about emergence, about possibility. They show us that oceans can exist without sunlight, that warmth can survive without fire, that chemistry can dance in the dark. They remind us that the conditions we consider rare on Earth, liquid water, internal heat, mineral interaction, may, in fact, be quite common elsewhere, tucked beneath icy crusts, pressed against rocky cores, hidden but not gone. And when a plume rises from a hidden ocean and reaches space, it carries a message across that boundary. It takes what is internal and makes it external. It offers a sample of a world's deep interior, placed gently into the night sky for passing spacecraft to find. That's a kind of invitation, an offering. And when we accept it, when we sample that vapor, analyze its contents, track its heat, we are accepting the invitation to wonder. We are saying, yes, we will listen. Cryovolcanism, then, is not just a phenomenon, it's a bridge between inner and outer, between past and present, between silence and motion. It even offers a bridge between disciplines. Geophysicists, chemists, astrobiologists, engineers, they all meet at the base of a cryovolcano because it speaks in all their languages. It speaks of energy flow, of volatile behaviour, of geological reshaping and biosignature potential. It speaks of systems, not just materials, and at a more human level, it speaks to our instinct to find stories in patterns, to listen for breath in stillness, to imagine warmth where there should be none. We find beauty in that, in knowing that even at the edge of the sun's light, on moons so far we can barely see them, something stirs, something rises. Not with noise, but with persistence. Cryovolcanoes tell us that motion is not always obvious, that change doesn't always announce itself, that some of the universe's most dynamic forces wear a cloak of quiet, and perhaps that's why we care. Not because these eruptions are dramatic, but because they aren't, because they require patience to detect, imagination to interpret, and humility to approach. They ask us to slow down, to measure with care, to listen longer than we usually do. In this way, cryovolcanoes align perfectly with the rhythms of deep time and quiet science. They are a reminder that not everything important is loud. Some of it seeps, some of it lingers, some of it breathes just beneath the ice, waiting for us to notice. As we near the end of our slow drift through the outer solar system, we find ourselves surrounded by moons that do not speak loudly, but keep their secrets close. They orbit in darkness, far from the warmth of the sun. They move slowly, quietly, with expressions carved in ice and time. And many of them, most perhaps, have not yet told us whether they breathe. These are the quiet moons that keep their secrets. Take Ganymede, for instance, the largest moon in the solar system. Larger than Mercury, larger even than Pluto. It has a magnetic field suggesting an active, liquid interior, a layered world with a metallic core, a rocky mantle, and, somewhere between them, a vast subsurface ocean. But Ganymede's surface is ancient, grooved, tectonic perhaps. Yet cryovolcanism here is less obvious. If it occurred, it may have happened long ago, or maybe it still does, in places we haven't seen, beneath ice so thick that not even gravity's subtle pull can easily betray the activity below. Or Callisto, Jupiter's distant battered moon, covered in craters, untouched for eons. Once thought inert, but recent data suggests it too might have an ocean, a salty one, slowly turning beneath an ancient shell. Yet no signs of motion rise to its surface, not a ripple, not a ridge. What stories lie beneath that silence? Even Iapetus, Saturn's two-toned moon, half light, half dark, has mysteries to offer. Its ridges, stretching like a seam across the equator, remain unexplained. Some have wondered if ancient cryovolcanism helped sculpt them. Others believe they are tectonic or the result of collapsed structures. Whatever the truth, Iapetus says little now. If it ever spoke, its voice has gone quiet. And then there are the Kuiper Belt objects. Beyond Pluto, dozens, hundreds of icy worlds drift in deep cold. Some are large enough to retain heat, to host oceans, to erupt perhaps in slow, syrupy mounds of ammonia-rich frost. But no mission has yet gone to them. No plumes have been seen, no faint warmth detected. They are enigmas waiting at the edge, each one a story half told. Cryovolcanism might be rare among them, or it might be everywhere, just subtle, erased by time, disguised by distance, hidden beneath thick, unbroken shells. The truth may take generations to uncover, instruments not yet built, missions not yet flown, but they are out there. Moons and dwarf planets and icy companions to gas giants, all keeping their secrets, some with oceans, some without, some with surfaces shaped by old upwellings. now frozen into place like forgotten thoughts. And we are learning how to listen. Our tools are improving. Our questions are more precise. Our missions now consider cryovolcanism not as an oddity, but as a natural process, expected even under the right conditions. We are slowly shifting from wondering whether cryovolcanoes exist to asking where they might still be breathing now. It's a different kind of question, one of optimism, of curiosity, of trust in nature's capacity to surprise us again. Because this story isn't over. We've barely begun to explore the outer moons. Even the ones we've visited, like Europa and Enceladus, have only been seen in fragments, brief flybys, low-resolution glimpses. But what those glimpses revealed has changed our expectations entirely. They taught us that icy worlds can be alive, that frozen shells can crack and exhale, that oceans can hide, then reveal themselves in vapour and warmth. They taught us to pay attention, to look for heat in the cold, for motion in the still, for breath in the silence. And so now, as we drift outward through the quiet beyond Saturn and Neptune, we don't just see frozen orbs, we see possibility. Every moon is a maybe with ice. A maybe with warmth, a maybe with something stirring beneath. And with each new mission, we move closer to those maybes, to listening better, to seeing more, to tracing the soft, slow rhythms of geology where light barely shines. Because this story, the one about cryovolcanoes and the moons that whisper, isn't really about eruptions or chemistry or even oceans. It's about attention, about the kind of quiet wonder that happens when we look slowly, patiently, humbly at a world and say, I see that you're silent, but I believe you may still be speaking. That belief is the heart of exploration. And cryovolcanoes, in all their hush and subtlety, are proof that even the coldest places can breathe. Even silence can rise. Even secrets given time may begin to speak. Ban Jun Noi. Continue ChatGPT Jun Noi. Wind down. Final 300 words. We've travelled far tonight. We began with a question. Soft, simple, but deep. How would we know if cryovolcanoes still breathe beneath distant moons? And from that single thread, we drifted outward, across cold orbits and quiet horizons, into the shadowed realms where moons whisper in frost. We touched the tiger-striped scars of Enceladus, traced the broken face of Europa, wandered Pluto's slowly shifting heart. We listened through gravity, followed the spectral hints of invisible plumes, and read the surface like a story written in time. What we found wasn't always certain. It wasn't always loud, but it was alive in its own way, because even in places that seem frozen, there are signs of warmth. Even when eruptions fade, the memory remains, in salt, in shape, in silence. Cryovolcanoes don't demand attention, they wait, and so we wait with them. Perhaps one is stirring now, unnoticed, on a moon we've barely seen. Perhaps the next mission will catch a breath in flight. Or perhaps, like much of deep time, they are content to move slowly, beyond our hurried gaze. Let's take a deep breath here, as they do. Let's picture a plume rising in the dark, lit only by starlight, curling upward into space and then vanishing again into the void. Let that image drift with you now, along with the hush of ancient seas, the soft pull of gravity, the patient motion of distant ice. Let it settle beside your thoughts. Let it soften your breathing. You're not alone in the silence. The cosmos breathes with you, quietly, always. Thanks for joining us on this gentle journey. Until next time. Now, close your eyes, if you haven't already. Breathe slow, and let yourself drift into the velvet dark, where even frozen moons still find a way to whisper.